Okay, so we're going to talk about matrix multiplication using shear memory. Remember last lecture we're talking about memory model, right? So we talk about global memory, shear memory, constant memory, and so on. So before we go in and talk more about a lot of these features, I'd like to at least take you through a very simple piece of code, which is the matrix multiplication that you just did, and talk about how you will be, one way of, how you can go about and use shear memory to really increase the performance of that piece of code. Let's kind of do a little bit of review here. Remember in the step 4 of the matrix multiplication, we actually do the device side kernel function. And in this function, we generate these kernels. And we're going to have, each kernel, the kernel will generate one thread that calculates one element of the result array. Remember, this thing is one of the, the threads. And the thread is going to be reading all these elements from the row and all these elements from the column and then do a dot matrix. Okay? So that's kind of, what this little, simple matrix multiplication does. Now, the problem with this thing is that all the threads access global memory for their input matrix elements. And they do it in a highly redundant way. Every input element is going to be read width times. Okay? So that is going to, to waste a lot of the memory bandwidth. If you do a little bit of calculation, you'll find out that for every floating point multiply add, which counts 2 floating point operations, you'll also be doing 2 memory accesses, right? So you read the 2 input elements from each array, and then you do a multiplication and you accumulate, right? So 8 bytes, okay? 8 bytes of data is single precision, so it's 4 bytes each, right? So 8 bytes total will be needed for 2 floating point operations. So that gives you essentially 4 bytes, okay, per floating point operation, or 4 bytes per second per floating point operation per second, right? Now, we know that this chip has about 86.4 gigabytes per second memory bandwidth. So this is the physical reality. Okay? You cannot pump more than 86.4 gigabytes per second through all the pins. And that gives you, if you divide it by 4, okay, that gives you kind of the upper limit of the gigaflops that you can hope to accomplish. If everything else worked perfectly, you will hit this limit, and you won't be able to get more than this performance. That's just the physical limitation. If you run this piece of code on the real hardware, you should be getting somewhere around between 10 and 15 gigaflops. Okay, so that's kind of, I don't remember exactly the number, so run it yourself and get that number. Do you want to give out a number, or you want them to just find out?
They can just find out. I don't know the number.
It's not hard to find out. Okay, so just right around that number, right? And he said, 15 gigaflops. That's a big number. That's more than let's say my salary in terms of dollars. So that's not bad, right? But if you compare that to the potential, right? That is, if I compare that with potential, meaning potential maybe what Bill Gates make every year, right? Then I start to think that maybe my salary is a very small number, right? So this is, if you compare that with the peak performance of the chip, which is over 300 gigaflops, then this kind of 15 or so suddenly becomes a very small number, right? It's all relative, right? So at this point you said, what? Is this really it, or this is something that we can do better, right? So this goes back to my comment at the very beginning of the semester. I believe that I can teach you to do parallel programming in CUDA in less than an hour and a half. Okay, And I actually figured out that there are a few things I can even take away from that lecture, 2, so that I can truly do it in an hour and 20 minutes. However, the only catch is that you will be able to do parallel programming after that lecture, but you won't be able to do the parallel programming at high performance. Okay, so that's really supposed to be the moral of the story at this point. So in the next 30 minutes or so, what I'm hoping to do is to teach you enough that you can boost this number by about 3 times. Okay, so that you can, get up to about, probably about 50 gigaflops. Okay, and that's a very nice investment return for 30 minutes of your life. How often can you boost your salary by 3 times by taking a 30-minute course, right? So it's not a bad investment in that sense. So the little idea that we have here is we want to use the shared memory to reuse global memory data. Remember, each memory element that we load, from the memory, we actually load it with times. So if I have 1K by 1K array, I will be loading each element 1,000 times, again and again and again and again and again, right? And so, one thing that I always, encourage my students to do, if you haven't done so, is that we keep using these numbers, hundreds, right? Thousands, right? And I really would like to encourage you to take 1,000 pennies. Okay, just take 1,000 pennies. Lay them all on the table. Okay, choose a pretty big table because it does take a pretty big table to do it. And you would begin to appreciate, what 1,000 really means. Okay, and so next time when we do a 4K by 4K array, I cannot really encourage you to do it, but if you like, you could do a 4K by 4K, coins, okay, and that would give you a very concrete feeling of how big these things really are, right? And that would give you some very, very concrete feeling about how to deal with these performance numbers. It only takes once. If you did it once, it will be with you forever. So if we load each element into shared memory and have several threads, okay? So, if we figure out a way to just load these things into the shared memory once, and then have a fairly large number of threads to just access the operands out of the shared memory rather than all of them going out to the memory, global memory, then, we conserve that memory, bandwidth, right? So this is the basic idea of, tiled algorithms. So how do we do something like this? Essentially, the issue is this. If I want to do it in a very, very, I would say, straightforward manner, I would say, what's the problem? What I would do is I would load the entire M array and the entire N array into my shared memory. Am I smart? What's the problem? What's the problem?
It's not big enough.
If I only care about 16 by 16, it may work, right? But it cannot handle reasonably large inputs. Right? You're absolutely right. So if I want to be able to multiply, let's say 1K by 1K array matrix, I won't be able to use the shared memory because I only have 16K bytes per processing element, right? I can't get enough of those. So I need to figure out some kind of compromise. I need to grab, some of them. If I don't grab a bunch of them, I may not be able to reuse. If I grab too many of them, I may not be able to accommodate all of them on the shared memory. So there's a little bit of a trick that I need to do in order to make that happen. So the general idea, it turns out that these things all have been studied, for many years by programmers, okay? None of these things are new. So in many ways, when you learn parallel programming and these tools, the first thing you do is you actually go and look at a lot of these patterns, essentially widely used tricks that a lot of programmers use, And you know what, you learn a bag of tricks, and you know, on top of them, you invent a couple of your own, and usually you're in business. So, you know, what we'll end up doing is we will chop up the input and output arrays into these tiles. Okay, so we just, you know, we chop them into these sort of, you know, in most cases, square tiles. It turned out that they don't have to be square, but you know, it gets more complicated if you don't use square tiles. And we will use a thread block to calculate all the results in one tile. Okay? So let's say, instead of just generating one block with width by width threads in the previous version, right? Now we say we're going to generate block width by block width or block size by block size threads in a block. And then we generate multiple blocks to cover the entire result array. So far, so good? Okay, so now we have a two-dimensional, we'll have blocks, and we have, you know, a grid of blocks, right? Now, so whenever we need to calculate, you know, let's say this thing, originally what we needed to do was we needed to do this and this all the way, right? But instead of doing that all the way, what we will do is we will first load this block here, the first horizontal block in N, and then the first vertical block in N. Okay, so we got these two tiles, okay, into the local memory. By controlling the tile size, we can determine how big or how small these tiles are. So we adjusted things in such a way that they can fit into the shared memory. It's under our control, right? So once we loaded these two into the shared memory, then we do the following. We have all the threads, okay, all the threads in the thread block to access all their inputs from the shared memory rather than the global memory. Okay? So we will just, you know what, so this guy is going to be multiplied by this guy as well as this guy as well as this guy, right? So all these different columns of the N array is going to, you know, essentially be multiplying with this guy, but they all come out of the shared memory rather than global memory. So once I'm done with that entire sweep for all the threads in the block, then I throw away these two tiles from the shared memory. I move on to the next two tiles, the second horizontal tile and the second vertical tile. I load them in once, and I continue the dot product for all the output elements from these two tiles. So I'm doing every dot product in segments, right? I do that first segment, and then I do the second segment, I do the third segment, and so on, until I'm done. So by doing this, I have the following advantage. If I manage to load each tile only once from the global memory into the shared memory, then I suddenly have block width threads, okay? Let's say if I have a 16 by 16 block, I will have 16 threads that all will access their input, okay, their input from the shared memory. So suddenly I have a 16:1 access ratio or reduction, right, from the original piece of code in terms of global access is concerned. I used to go to the global memory for all the 16 usages of this thing, but now I'm going to be able to, you know, have all the 16 of them to access their input from the shared memory. It's not ideal because if the original matrix is 1000 by 1000, theoretically I can reduce the ratio to 1000 to 1, right? Because I have 1000 to 1 redundancy. But by choosing a block size of 16, I will only be able to do a 16 to 1 ratio. If I choose a bigger tile size, I can increase the tile a little bit more, the ratio a little more, all the way until I cannot increase that size anymore, right? At that point, I'm limited by the shared memory size. So the limit, of course, ideal limit is, if I can increase the tile size to the entire array, then I can remove all the redundant loads, right? Which makes intuitive sense, right? But I just don't have enough local on-chip storage for doing, for that kind of, luxury. So this is the basic idea, okay? Instead of computing, computing the entire dot product in one loop, I'm going to actually break it down into segments, and each segment is going to be a kind of a loop iteration, back into this tile thing. And we're going to go through the code example to kind of just make it a little bit more concrete. And beyond that, we're going to still be generating the same number of threads, total number of threads, because each thread block has a fewer number of threads because it only covers one tile worth of threads. However, we're still going to generate all the blocks, the thread blocks at the same time. So these thread blocks will form the scheduling units, or the sort of the assignment unit into the SAMs. And any of these blocks can go into any of the SAMs. So let's say if I have 1024 by 1024, and we're doing a 16 by 16 tile, then we will have 8 blocks in each dimension, right? And we have 64 of these blocks, and each block will have 256, which is 16 by 16 threads. And we're still going to be generating all these threads. It's just that the unit of execution and assignment into these SAMs will now be in terms of 256 units. Okay, you're going to be throwing 256 threads from this tile into one of the SAMs, another one into another SAM, and so on. This also goes back to the problem with the original code. Remember, the original code has only one block, right? And by definition, how many SAMs can that piece of code use? Right? So right from the beginning, you're only using 1/16 of the execution resources to begin with. That coupled with the memory bandwidth limit, you're not going to go too far with that piece of code, right? So with this two-dimensional structure, blocks of threads, and and then the threads in the block, then you have a much more balanced usage of resources in your execution. Okay? Now, so let's go into this a little bit sort of more from the engineering perspective. I just told you that each SAM has 16K bytes of shared memory. So what I would do is, if I use, let's say, 16 by 16 tiles, then I have 16 by 16, which is 256 elements. Each element is 4 bytes. And I need to have M and N tiles, right? So I need to have 2 tiles. So that's 2 times 256 times 4 bytes. And that gives me 2 KB of shared memory usage per thread block. Okay? And that is a 16 by 16 tile configuration. And we can potentially have up to 8 of these thread blocks actively executing because there are 8 2 KB units in the 16 KB. So from the sheer memory point of view, if we use 16 by 16 tiles, we can execute up to 8 thread blocks per SM. Okay, so that's the limitation as far as the sheer memory size is concerned. Okay, so for block size 16, and this, if for the 16 by 16 tile, and so on, this allows up to 8 times 512 loads. Okay. So remember, we have 2 loads per. This is the initial load thing, right? I should talk about the initial loads first. Then. This is something that I forgot. Okay, let's do this. So if you think about it, you say, well, you know what? In order to do this computation for a 16 by 16 tile, I will need to be able to load all these 256 elements of M and 256 elements of N into the shared memory. Okay? So that's 512 of those global memory loads I need to do initially to get all these data elements into the shared memory in preparation for the multiplication and addition. And that tells me that I will have 512 of those loads, okay, from the global memory before I would into the shared memory so that I can prepare for the multiplication. Given the fact that I can have 8 blocks run on the SM at the same time, I can have 8 times of those loads. Okay, 8 times of the 512, all trying to load from the global memory. And what this means is that I will be able to essentially issue all the 4,096 loads to the memory. Okay, I would do one block, I issue all the loads for that block, and then I would switch to another block, I issue all the loads for that other block. Remember, the memory can take hundreds of cycles to finish. So I can actually issue all the 4,096 loads into the memory, and therefore overlapping the latency of all these loads. Okay? And I can actually perform these, memory latency tolerance. And that gives me a lot of, latitude in tolerating these memory latencies. However, in practice, there will probably be half of this due to scheduling to make use of these SPs, and I'll talk about that later. I'm purely talking about this from the sheer memory size limitation point of view, and I will give you some other practical limitations about how many blocks, for example, that an SM can actually accommodate in the physical implementation of GTX. If I increase the block size to 32, I would need to have 2 times 32 times 32 times 4 bytes shared memory usage now. And so that's only 8 KB. As you were alluding to, I can still have enough shared memory for that tile size, right? However, that it allows you to have only 2 blocks now. Okay, only 2 blocks of threads. And it turns out that if you have only 2 blocks of threads, it actually changes the efficiency of your scheduling. Okay, so in that sense, you will likely see less effective, tolerance of memory latency because you don't have as many blocks that you can switch around. Okay, and we're going to actually take you to some of these things. In general, up at this point, you should just feel free, okay, to try the 32 anyway. Okay, and let me know what you find out, and we will go deeper and deeper into these things, and you will know exactly what's going on. Yes. When I increase my block size from 16 to 32, I increase the reuse factor of every memory element by 2 times. Because now every memory element is reused 32 times rather than 16 times. So I further reduce the memory factor. However, I kind of reduce some of my scheduling flexibility. I don't have as many things to schedule from as I had before. So the issue is, if you lower the block size, then you increase your scheduling, flexibility, but you reduce the memory reduction factor. It turns out for this piece of code, 16 is actually the optimal. Okay, I'm giving you the answer now. But you know what? If you try it yourself, you would begin to see that this is something that you should actually play with it a little bit at the beginning of the semester, so that you build up a little bit of intuition. It turns out that you also need to understand a little bit more about the scheduling in order to actually reason about it. So at this point, I would expect that you just see, okay, increased memory factoring, reduce the scheduling, flexibility. So there should be a sweet spot. You try it out, you probably come up with 16. Okay, at this point in time. So there are some first order things that, kind of rule of thumb kind of things that you need to, that I want to expose you to. And in a few lectures, you will know how these numbers come about. Okay? So, the first thing is, each thread block should have about 192 threads. Okay, a minimum of 192 threads. And this is not something that that I could easily explain without showing you some of the lower level details. And by the way, this is just an 8800 GTX microarchitecture. It may change in the future. On this machine, we want to see about 192 threads per block, and the block size of 16 gives about 256 threads, so it's kind of above that threshold. So that's kind of a threshold that you want to go over. And you want to have a minimum of 32 thread blocks on this machine. That is, you want to have a minimum of 2 blocks. Okay, in each SM, right? Remember, there's 16 of them, so we're talking about 2 per SM, and that's the minimum that you need in order to just be able to play. Okay, and so let's say 124 by 1,000 by 1,000 matrix gives you 64 by 64 blocks, and that gives you 4,096 thread blocks. That's plenty, okay, to saturate this machine. So if you have a 1K by 1K matrix multiplication, you should get a pretty good performance out of this piece of code. And each thread block perform 202. But the flip side of the story is that if you are multiplying, let's say, a 64 by 64 matrix, okay, if your input is 64 element by 64 element, you should not expect a very good utilization of your machine, right? Because you can only have 4 by 4 thread blocks, 16, and that's just not enough to really saturate the hardware on this machine. And each thread block performs, 256 times 2 floating point operation. If you look at the thread block per tile, this is actually per tile. Remember, we have 256 each thread block. Thread block loads. Each thread block will perform 256 times 2 loads for the tile. It is loading 2 tiles for each step. And for the data in those 2 tiles, it will perform 256 times 2 times 16 floating point multiply or add operations. And this is, essentially, everyone is going to be, there's 256 result elements, And each element will require, 16 of the 16 pairs of dot product within the tile. So for every tile loaded, you will have so many memory loads, and it will perform so many multiply or add. And if you calculate it out, the ratio of computation to memory load just got reduced by 16 times, right? And that gives you a high enough compute to memory access ratio that the memory bandwidth suddenly has been suppressed, usage has been suppressed enough that you're not going to be able, you're not going to be limited by the memory bandwidth anymore. So let's kind of quickly go into the CUDA code and just kind of show you, what you need to do for MP2, right? So you would declare the dimension of the block and the dimension of the grid. So the dimension of the block in this case is block size by block size. Could be 16 by 16, could be 8 by 8. You can vary that number, right? And then you can actually declare the grid dimensions to be the width divided by the block size, and then the width. These are all initialized by that constant width anyway. So this is all good. You're going to also have the width divided by the block size. Now, since we're talking about square matrix multiplication, all these numbers are, both of these numbers are the same, both of these numbers are the same anyway. As we mentioned before, for very large n and m dimensions, you will need to add another level of blocking or another level of tiling to execute a second level blocks sequentially. So you will need to add essentially another level of loop at the outermost level to iterate over the maximal grid size that's allowed. Okay, so if you really want your program to be totally general, then you need to add that level. But we probably were not going to require that. If you look at the kernel code, so remember the kernel is now supposed to generate 2 levels of threads, right? The blocks and then the threads in each block. So if you look at the kernel is going to have access to the block ID X and block ID Y, index Y, and these are the special variables that allow the threads to know which element it is supposed to be working on, right? And you also have the block ID and essentially the index and the thread index. So these things are all going to be used in memory accesses later on. And we're going to just essentially do a initialization and initialize the p-value to 0 in preparation for the matrix multiplication. And then we're going to kind of just loop through. This is the outer loop. Now it actually loops through all the blocks. Okay, because we're doing one tile at a time. So we're going to loop through the tiles. Okay. So basically, the code is going to iterate through these tiles. Okay, from the outer level, we're just iterating through these tiles. And then within each tile, we will be doing the dot product or the segmented dot product. So in order to do to use the shared memory, what we will do is we actually will use the threads to cooperatively load all the input elements into the shared memory. Okay? So if you look at the picture here, remember we have block size by block size threads, right? Each will be accessing block size by block size input tiles. So at the beginning of the of each tile, I can just use one thread to load its corresponding input elements here. Okay? That's not the only element it's going to use for computation, but that's its responsibility for preloading. So essentially we'll have so many threads, each one will be loading one element, okay, of n, and each one will be loading one element of n. So we only need to have 256 threads, each one loading, one of the 256 m elements, and each of the 256 n elements. So the first phase of the kernel is to load up. Okay, so to load up the corresponding shared memory location, and this is get matrix element m sub and tx and ty. This is actually just a macro, and I actually gave you the code later on. It's just an index into the global memory and then find the corresponding location. I just use a macro to make the code a little easier to read. So you go to the big matrix in the memory, find the element that you're supposed to load, and load it into the corresponding tiled position of the shared memory. Put it in. Each thread is responsible for one m element and one n element. Everyone will be executing this statement in parallel. Okay? Conceptually, they're all executing in parallel. So you will be doing the n load and the n load. What this is that, remember we have 256 threads. All have, each one has 2 loads pending, right, into the memory, global memory. These things are random, okay? You don't know how long they're going to take. Some of them will take longer than the others because of the DRAM paging and, DRAM, the bank conflict and all that stuff, right? So you don't know exactly which one will finish first and which one will finish, last. So you will do what we call a barrier synchronization, meaning that all the threads, after they dispatch those 2 loads, they will hit the sync thread function call, okay? And this thing is a barrier synchronization in the sense that it will actually keep getting, so all the threads will actually just all eventually get to, after they issue the loads, they will actually come here, okay, only after they are done with the loads. So this barrier synchronization will make sure that all the previous instructions of the thread are complete before they will allow the thread to leave the barrier. It also will make sure that all the threads can be released before they will release the rest of the threads. So all the 256 threads will actually be waiting at this position, okay, at the instruction position, waiting for 2 things. One is all its previous instructions, its own previous instructions are done, which means those 2 memory loads, right? And also all the other threads are done, right? So only when all the 256 threads all reach that position and all done will they come down to execute the next phase. That's exactly what barriers mean. And that means that before you go and do any multiplication and addition out of your shared memory, all the 512 input elements that you need are already there, right? So this is the reason why you need to have multiple blocks, because you can easily have a situation where all the threads in one block essentially get stuck in the barrier synchronization, right? So you can quickly get to the point where all the threads are all waiting in the various barrier, right? So if you have only one block, let's just kind of go through the scenario. If you have only one block, you will be seeing all these loads, right? And there's no usage of the multiply or add function units, right? During that period of time, there are only loads. Make sense? And you barrier sync. And at that point, a lot of these threads will not be able to make any progress. They're all waiting for other threads to finish, right? And then you go into this phase where you do the multiplication and add out of the shared memory. You're not using any global memory bandwidth, right? So you have another phase where you're underutilizing the load and store, the load bandwidth, right? So one block of threads is definitely not a good idea because you would be going into imbalanced machine usage through these phases. Two will be better, right? Because conceivably you can have, one batch, 256 of those going through the barrier, but there's another one that you could keep issuing memory loads, right? So depends on how quickly the first one move into the multiplication and add phase. You may actually have both pretty much stuck in the same place because it may take longer for the first group to finish before you can actually before you can move these into the multiplication. They still essentially get trapped in the same stage at the same time. But if you have more groups, chances are some of the groups will be moving into the next phase, while the following groups are trapped in the first phase. And when that happens, you start to have a more balanced machine usage. You will have some of the earlier blocks using multiplication and addition, and you have some of the later blocks doing the memory loads, right? Suddenly you start to use the machine resource twice as well. So that's why, in general, 2 blocks may not even be sufficient. You may need to have, 3 or more in order to actually reach that kind of pattern, okay, statistically. Now, so this is the phase where everyone will be busy doing multiplication, addition, accumulation to calculate the segments of dot products. And then you will go and actually synchronize again, because this synchronization makes sure that the computation is done and you're truly done with all the inputs, okay? You're truly done with all the input elements in the shared memory before you go to the next iteration. The next iteration will begin to overwrite those input elements for the next iteration. So you need to make sure that every thread is done. And it's not just you're done. Remember, there's 15 other threads using that same element, right? So you need to make sure that they're all done. So that's why this barrier synchronization will be done again. And everyone will be waiting here for that multiply add loop to finish, not only for itself, but also for these other threads. So, once we're done with this, that entire loop, then, after we iterated over all the tiles, then we're done with all the results, okay? And these results will be written, essentially will be, written back into the result. And then we are done with the whole multiplication. And this code should run about 45 gigaflops. Okay? There are 2 reasons why this code runs 3 times faster. The first one is obvious. You just cut down the memory bandwidth requirement by block size factor. And the second one is you just created a lot more blocks, rather than just having one block. So you're making much more fuller utilization of all your execution resources and SAMs. Now you're using all the 16 SAMs rather than 1. Okay?